Please proceed.
All right. Good morning and good evening, friends from United States and Taiwan and around the globe, I assume, but I think not today. Welcome to Data and Analytics Colloquium this evening. I just want to thank you for joining us. And before we start, just as usual, let me just briefly introduce to you the deck. We short it as the deck, Data Analytics Colloquium. This is supported by National Chongqing University, College of Law and Politics in Taiwan, and the University of Texas at Dallas as well. And then this colloquium, actually, we try to invite international scholars and data scientists in this is an online seminar format. So members of the colloquium will engage in conversation with the speakers, and these speakers are all the top-notch speakers, as you can see from our past invitation list. Just like today, we have Jeff Gill, Professor Jeff Gill, and he's a well-known professor and scholars. So this is you can check from his portfolio, and you know how good he is. I can say that. And also, we have.
Uh-oh. You get muted.
I need to use the microphone sometime. Okay, can you hear me now?
Yeah.
Okay. All right, and sorry about that. And I was mentioning Professor Harold Clark, and he is also our advisor of this colloquium, and we want to thank him for joining us tonight, so we can have a more conversation and exchange in this today's talk. So this, I think I have spent enough time, but once again, I want to welcome you to join us. In case that any one of you missed the previous speeches, and please check online. We do have the website, the Data Analytics Colloquium, and then we have the previous talks on the YouTube channels. So please find time and check back all those videos, and you will be surprised how many good stuff there, you know, in those previous video clips. All right, and so let me turn my microphone to Professor Carl Hope, and he's the co-host from UT Dallas, and he's gonna give you an introduction to today's distinguished guest. Yes, Carl.
Hello, thank you, Peter. Thank you for letting me introduce our guest. This is really a big privilege. We have two very famous political methodologists coming aboard to give this speech and also have a rejoinder. And allow me to introduce Professor Jeff Gill. And Professor Jeff Gill is a distinguished professor in multiple departments of American University. He is in the Department of Government and also in the Department of Mathematics and Statistics. And also he's the member of the Center of Behavioral Neuroscience at the university too. He recently founded the Center for Data Science, and he has been involved in also advising, consulting in many projects, including recently medicine projects or neuroscience projects. And his famous book on Bayesian research is also well cited, one of the most citable. And today he's going to talk about a topic called political science of data science, and he will be basically expanding on his article published earlier this year, Journal of Politics. Now, joining him will be Professor Harold D. Clark, an Asbo Smith professor at the University of Texas at Dallas. And Dr. Clark has been one of the most prolific methodologists that I know of, and I think he's one of the top in the country. And he has been editor of multiple journals in electoral studies, PRQ, Political Research Quarterly, And now this is really, really a great opportunity. We can convene these two famous scholars, and Dr. Gill is going to present on the topic of political science and data science, and Dr. Clark is going to join him and discuss his article at JOP, and both of them will share their visions about data science in political science or political science in data science. Then Professor Gill prefer a format which is more informal. You can interrupt with question, or you can post a question on the chat box, or you can just ask him a question at the end of that presentation, and also the dialogue between them, and or you can join the dialogue too. And without further ado, allow me to introduce Professor Jeff Gill, American University. Thank you.
Thank you very much, Dr. Ho, and thanks everybody for inviting me and having me today. I'm going to move over to my slides, and you tell me, is that working?
Yes.
Working.
Good.
Here,
the bad news is I can't see anything else but the slides. So, Carl, you'll have to jump in and tell me if there's a question or something.
Sure, I'll do the moderation. Yeah.
Okay, excellent. Thank you. Some things to think about as we progress into the 21st century. This is the data century. Whether you like it or not, this is the data century. Things that this affects our personal lives, our careers, our children, our future prospects. These are all intertwined with the way data are collected, stored, and used by others, whether those others are humans or computers. And it turns out that governments have mostly lost control over this process. The macro economic political forces have subsumed the government's, most, if not nearly all governments' ability to have control over this process. So what this means is, like, from a personal standpoint, is the more education you have in data science, big data, statistics, the more you understand data privacy, the more you can exert some control over what other people are doing with your data. So this is an interesting period in human civilization. So we are only about 200,000 years old, depending on which anthropologist you talk to in our current form. And an amazing thing happened in the last century, in the 20th century. Over that 100-year period, average life expectancy of humans around the world increased by 30 years. And that had never happened in the history of human civilization or biology. So basically, we're in the middle of a new and fifth major revolution in human history. So there was as you see here, the Upper Paleolithic, where we first started farming as people. The second one was more or less when tools became applied to that process. The third is the Industrial Revolution. Obviously, that's well known. Now we're in this information revolution, or this data revolution, and you see I have some question marks there. I think the next revolution is going to be the DNA revolution, but I don't know that for sure, obviously. But the interesting thing, and the reason I have this slide, is people typically, when they're in a human revolution like these that you see here, they're typically not even aware of it. They're basically just trying to live their lives and feed their families and have careers or whatever is going on at that point in human history. But I want to just point out that we are, and we should be aware that we are, in the middle of the fifth major revolution in human history. And so everything around us is changing much faster than other humans had ever experienced. And not just things like pandemics and political events, but how we work, the environments we work in, the way people do their work in professional settings. It has never moved faster for any other set of humans than currently. By the way, as Dr. Ho pointed out, this is stuff mostly from my JOP here. I'm obviously not going to talk about everything, but I'm going to pull out some parts that I think. Somebody's echoing me.
Hi, Jeff. I already posted your article to the chat box, so everyone should have the access to that.
Okay, fantastic. Thank you. Okay, so it turns out the rest of the 21st century, this is going to be a century where major progress will be made in the social and biomedical sciences. If you think about the last century, that was where major progress was made in engineering, chemistry, and physics. Okay, so the list of human accomplishments around those three fields in the 20th century is startling. Putting men on the moon, developing programmable computers, all the way down to the hydrogen bomb, if you consider that a human progress. And so it turns out that that is social scientists and biomedical scientists, turns out we need computers more than the engineers, chemists, and physicists do. It turns out the computer that planned the trajectory of the Apollo missions to the moon had about the same power as 2 Nintendos, okay, today. So imagine putting men in a metal can and sending them to another off-world environment using a computer that we would consider to be relatively dumb today. And so the reason that we need computers more than they did is because the hardest things to study are humans. Humans are incredibly difficult to study because they're unstable. They lie, they take drugs, they don't take drugs, they drop out of surveys, they drop out of clinical trials, and so on and so forth. Whereas what most physicists, chemists, and engineers do, they control their subjects to a huge degree. So the key to future research, as you see here, will be digital computation and how we do it, data analysis and how that progresses, and the infrastructure that supports these efforts. And that includes storage and networking and other important aspects. But there's also another aspect of this, which is data access. That is, who gets to get what data? And as a researcher in both the social sciences and the biomedical sciences, there's data I need, and sometimes I can get it and sometimes I can't, and it defines characteristics of humans that I want to study. Integration of disparate data resources will also be critical. That's ongoing in the corporate environment at an incredibly torrid, fast pace. And then, of course, there are issues with long-term preservation of data. And we, as in humans, haven't had to worry about that before because preservation of data up until about the middle of the 21st century was on paper. And that was sufficient for the most part. But it turns out, like some things that we take for granted, in fact, if you burn your data onto a CD or some other physical structure like that, that's not going to last forever. It might last a long time, but even something like that, or an electronic hard drive, is not a permanent storage vehicle. And of course, the size of the data that I'm about to talk about matters in that regard as well. So, so some of the older of us will remember that for quite some period of time, data was a rectangular file with data dictionaries and a PDF codebook. In fact, in the old days, when you got your data from ICPSR, this is prior to my career, your university would get a tape that they would mount on a computer, and you'd get a tan-colored PDF, or not a PDF, printed codebook. But now we have very diverse types of data that we're interested in, both the social and biomedical sciences. Of course, genetic genomic data, which is large and at times unwieldy. Video is a very active research area in the social sciences. We published a wonderful article recently in Political Analysis where the scholar literally watched C-SPAN recordings of the United States House of Representatives and coded up every single time somebody from one party walked across the aisle and talked to a person in another party. And so it was based on video, but it ended up being a really interesting project. Geocoding and GIS, I'm going to talk about some challenges today. That's often high volume, large data. Imaging in the general sense. A former PhD student of mine, she works with images where she has developed software to gauge the level of violence that's shown in a picture. So Does Al Jazeera show more violence than the BBC and the New York Times? And questions like that can be asked. High frequency sensor data is a huge area, both commercially and academically. We are being monitored. I'm going to talk more about this in a few minutes. We're being monitored almost all of the time. Internet traffic data as a data set to study, not the content necessarily, but where it goes and how much goes where is another type of data that's increasingly being used in these fields. Mobile phone tracing is both useful and scary. There's a really interesting pair of articles in the December 2019 New York Times where they found that anybody can purchase gigantic data sets of people's phone usage, not their names, but their phone number and where they've been physically. And they used it to find one person in particular that was interesting. It turned out it was a person who was in the United States Secret Service working at the White House. And then they were able to find that person's home. And then they were able to find that person's wife's phone and then their kid's phone. And they figured out where the kids go to school and where the wife worked and what days and what hours he worked at the White House. And anybody can buy that data. And there were also other people they studied. But I encourage you, if you're interested in that at all, to go find that. It's not hard to find. And then, of course, a big area of development is unstructured text data. And particularly in political science, this is a very hot area. And we get a fair amount of manuscripts at political analysis on that. But there's also new sources as well, not just types. Of course, social networking and media. And there's a lot of work in political science. I'm sure you all know that on social media data. An interesting area that I'm very much involved in is human physiology data. That is monitoring people with devices. And so like one project I've been doing for years is putting accelerometers on people. These are just motion activity detectors. And it started, well, I had a cancer grant, and we were concerned that after prostatectomies, the physician will always tell the patient that they will get back to normal faster if they exercise. And every patient will sit in their physician's office and say, yeah, sure, I'll do that. And we wanted to know, do they really do that? And the answer, of course, is not always. But I had some accelerometers sitting around one year, and there was an election coming up in the United States. And so I put accelerometers on voters. And it's kind of a data set in search of a theory. I haven't done much with it, but it turns out I had it on 72 hours, the day before the election, the day of the election, and the day after the election. And it turned out that people were more active the day after the election. And my sort of rough interpretation of that is that they had more to talk about with people around the office, around the university, whatever. A big development here in Washington over the last decade is integrating government administrative records from disparate sources. Of course, transactional financial information has always been an important area, but now it's a very high volume area. And electronic human monitoring is related to what I just discussed. And these are both qualitative and quantitative, as you see. But in many of these cases, we need new documentation and archiving. That is, how do we store these things for a long time? How do we describe them to each other? And of course, you can see from my last bullet point, there's lots of privacy and confidentiality issues surrounding this generation of these new types of data. So I want to just think about numbers for a few minutes. I got these numbers last summer, so they're already out of date. But if I got them yesterday, they would probably be already out of date, but they're a good picture. So every single day of every single year, about 23 billion texts are sent around the world. About 5 billion searches are made. I love this, 40,000 per second on Google alone. 500 million tweets every day. About 300 billion emails are sent, right? I think a lot of that is spam that comes to me. 4 petabytes of data are created on Facebook every single day. I'm going to talk about bytes in a few minutes. 4 terabytes of data are created from each connected car. Most people don't know this, but if your car was built in roughly the last 5 or 6 years, the car manufacturer is collecting data on every aspect of how that car is used. So if you buy a Mercedes or a Ford or whatever, your car is constantly beaming back how you drive, the speed, how hard you brake, how far you drive every day, and more than you can imagine. It turns out the car companies haven't quite figured out how to monetize that. But I'm confident that they will as soon as someone's interested in it. Most likely, the insurance companies are first. 65 billion messages a day on WhatsApp, and 360 terabytes are uploaded to YouTube, which is stunning. A few more facts. Almost 22 million gifts are sent via Facebook Messenger, 149 billion spams a day, right? 222 million calls on Skype. This one doesn't surprise me. Venmo processes $75 million of peer-to-peer transactions. The next one's kind of weird. So the Weather Channel gets 2 times 10 to the 10 forecast requests. That's a staggeringly big number, but a big part of it is driven by other companies that are generating or producing content for us are querying the Weather Channel automatically over time, constantly. 65 million Uber bookings. That took a hit, of course, during the pandemic, at least here in the United States. Every day, the average person generates 10 to the 18 bytes of data, whether they know it or not. Just every time you interact with anything electronic, every time you walk down the street in many places, you are generating data that someone cares about. And I love this. The CERN Large Hadron Collider in France and Switzerland generates 864 zettabytes a day when it's operating. I think right now it's being upgraded. So just to give you a context on these numbers that I've been quoting here, I'm going from a bit at the top down to Chom's byte down at the bottom. And you know, it's funny because I remember when a megabyte was considered a reasonably big quantity, and certainly I remember when a gigabyte was considered a big quantity. But now people throw around terabyte, petabyte, exabyte as if that's just normal. And you can see we're going down this structure here as humans generate more and more data. I don't know where these names come from, but they're kind of amusing. A yottabyte and a brontobyte and a zatzabyte and so on and so forth. But we are generating a staggering amount of data as a civilization. So that leads to the question is, what is big data? The true but sort of flippant answer is it's basically what anyone wants it to be or says it is. Many of you, I'm sure, have seen the classic definition: volume, variety, velocity, value, and veracity. And if you look hard enough, people have added other V's to that list, but those are the classic ones. Meaning, how big is it? How different is it? How varied is it? How fast does it come at us? How, you know, what's it worth? And how reliable is it? But my definition is a little different. As you see here, my definition is big data is data that's large enough to challenge whatever the computational resources are at that point in human history. So it turns out that the abacus was invented about 4,000 years ago because people had a big data problem, right? That is, in financial transactions at a market or a bazaar or something of that sort, they needed something to calculate change in prices and so on and so forth. So in the Middle East, at the time, they invented an abacus. Now, if you think about it, that's just a basic computer, but it was built because they had this big data challenge. So if you accept my definition there, on the next bullet point, you see, that means that humans have always been in a big data era, right? We've always been confronted with data that we need to have devices, at least once we started producing devices, to understand better. So the current digital universe, when I last looked, was estimated to be 44 zettabytes. So if we go back here, right, we're down to 1,000 to the 7th power, which is a fair amount, of course. And so projections, you know, these projections are a little fuzzy because different people calculate or predict things in different ways. But I recently read that before 2025, we'll be producing 463 exabytes of stored data every day. So, you know, if we live in this era and where we can't not live in this era and we can't not have to confront big data, what are some of the tools that we might think about? or some of the issues, I should say. So at this point, I think I don't have to explain blockchain. Blockchain continues to be an extremely important a transmitter and other processor of data. It's used by governments, corporations, and so on and so forth. You see stories about the regulatory issues pop up every once in a while. The GDPR from the European Union is probably the strictest protection for human citizens' data. The US is probably the worst in terms of laws and regulations to protect people's data. AI and various invasive apps, they know more about you, like my car example, than you have any idea that they know. Your insurance company is spying on you. Your hotel is spying on you. Your car rental company is spying on you. I figured that out myself when I returned a rental car a couple of years ago, and they told me where I'd been at the counter and how far I'd driven. You know, like, oh, okay. Was I speeding? Augmented reality and virtual reality, which are different, by the way, this is becoming more than just gaming. I read an article that Apple is about to come out with an augmented reality pair of glasses. That'll be interesting. So edge computing is a term that I'm not sure a lot of people have heard. It's Internet of Things that watches you all the time. So cameras on the street, various things that corporations do to their employees, meaning things like monitoring their web habits, so on and so forth. That's called edge computing because it's on the edge of the computing environment. That is, it's right in front of the person. Interesting enough, despite this gigantic, phenomenal leap in data being generated, less than 1% of all the generated and stored data are being analyzed. That is, like somebody or some machine is doing something with them. And an interesting thing about that is the rest of that sentence. This number is less than 1% and it's going down. And the reason it's going down is humans are generating data at a much faster pace than we're generating tools for analyzing the data. This is, of course, is a huge market. I've seen at least one estimate that it's over 500 billion in business worldwide. I'm convinced that that's a bit low, but I'm unable to find a more reliable estimate. Again, these things change so fast that my numbers that I'm quoting here are approximations, and probably low approximations. So a question that I guess I get asked all the time, particularly since, as Dr. Ho pointed out, I started a Center for Data Science here at AU, is this really a field? And I think the answer is absolutely yes. Every university that I know of in the United States and many internationally, including UT Dallas, of course, has a data science center, a data science department, a data science degree, or some such endeavor like that, and maybe multiple endeavors. So here at AU, and I can talk about this later, the Center for Data Science is a research center, but I also co-direct our fairly new, it's 3-year-old's master's in data science. And this thing went from 0 to 100 students in 2 years. Now, keep in mind, we're inside the Beltway here in Washington, D.C., and so interest in this is just phenomenal. So it's an atypical environment in some regards. But the parents are really of data science are computer science, mathematics, and the social sciences. And the last part of that sentence is the one I want to emphasize because the first part is more obvious. The reason the social sciences are so important, including political science, of course, is that I would estimate over 95% of all data science work is done to study humans, people. And, you know, that's, as you see my list here, socially, politically, biomedically, and in terms of dollar amounts, most importantly, commercially. So if data science as a field is tied to the social sciences as a purpose, we should recognize that. Now, having said that, there's an amazing shortage of data scientists around the world from various employers. And I like to tell my master's in data science students here that there's no such thing as an unemployed degree data scientist. That animal just does not exist. I've never met one. I've never heard of one. I've never seen one. And the job prospects are just phenomenal. So, we see masters and data science students commanding six-figure incomes right out of their programs. Here's just an example I cut and pasted from a little while ago. It's fairly typical. You can see the required skills down there. And that's a pretty obvious list, to be honest. One of my favorite facts, and it's a little dated, but I'm going to keep it on the slides forever. The Harvard Business Review, as you see here, said that the data science is the sexiest job in the 21st century. I just love that. I've never had anything about my work being described as sexist before. Actually, that's a typo. It's not the sexist job. It's the sexiest job. It turns out there's a big difference, right? I need to fix that. Note to self. Yeah, but it is according to them the sexiest job. Okay. There's a
recruiter. Interrupt. I have a lot of students. They are really good ladies in data science coders.
And Glassdoor is a big recruiting company here in the U.S. And every year they rank the best jobs that pay over six figures. And this year they ranked data scientists as the #2 best job in the United States that pays over 100,000. And the funny thing about that is that the #1 job is JavaScript programmer, which could almost be the same thing, right? So you get the idea. When I looked this up, there were about 30 million ads for data scientists in the US alone last year. IBM estimates that there's something like a 40% shortage. But there's another interesting trend that may affect some of us on this call or whatever, is there's an increasing trend for the big technology companies to hire PhD social scientists, including some of mine. A former PhD student of mine works for Facebook, for instance. And there's a couple of reasons for that. One of which is the top of this slide, right? Which is that data science is really a science about people for almost all work in data science. But there's another reason, which is interesting. So those companies obviously hire armies and armies of computer scientists, but from high school through postdoc, computer scientists don't really study an important applied problem. They're busy developing and learning tools and theory. And so what those companies have realized is that there's a huge need for technical social scientists. What I mean by that is people like political methodologists, people like Harold Clark, okay? To be able to talk to both the computer scientists and to say, here's an important problem we want to solve about humans, about social interaction, about commercial interaction. And so this is an increasing trend, which I think is a great trend. So for years and years and years, one of the reasons that economists were paid more than political scientists on average is they had a commercial labor market and we generally did not. And that is clearly changing in political science. And there's plenty of evidence of that. So that should please anybody out there who's still in graduate school.
A little bit. Can you elaborate about the difference between computational social scientist versus what you talk about political data scientist, or maybe a data science in political science? Are they the same thing?
No, but there's certainly there's a big Venn diagram intersection, right?
Mm-hmm. Yeah.
So social science is obviously a very broad category, and it includes everything from what I do to the other end of the scale, where people are interviewing people in villages in some part of the world and writing qualitative papers. But I think there's really sort of, I wouldn't say it's a hierarchy, but there's sort of a distinction around the use of computation. Mm-hmm. There are plenty of political methodologists who use pretty basic computational tools, like say Stata, right?
Yeah. Yeah.
But on the other end of the scale, if someone tells me they're a computational social scientist, what I infer from that is they're using the tools in this required skills list up slightly above that point, right? Mm-hmm. That they're running large scale simulations, Markov Monte Carlo. That they're doing data mining on gigantic data sets, or they're doing statistical genetics, which, by the way, has an increasing social element to it. We now know that there are epigenetic effects from various behaviors and interactions and whatnot. So in my view, sort of sorting out those categories, and again, it's hard to sort out because there is a lot of overlap, is based on the use of computation. And keeping up with the use of computation is a time-consuming job, right? Because tools come out every day. I would say once a week, at least once a week, somebody either at my university or somebody I interact with at the journal or otherwise tells me about a new tool that I've never heard of before. And then I go look it up and I see if I'm in, something that I'm interested in learning or not. But I mean, if once a week I hear a new tool, this is just a really fast charging, fast moving environment. Carl, does that answer your question?
Yes.
Okay.
Thank you.
So how does the data science century or data century affect us, as academics? So we have, again, interesting data or bigger, more complex in ways that I've described and more. This is a very, sort of high level talk. Interesting enough, there's been huge progress in qualitative data analysis, and I'm including text as qualitative data, in fact. We need more in that area, though. One thing I've noticed is a lot of social science departments in the US and around the world, they typically don't have the large and expensive infrastructure that you see, say, perhaps in an engineering department or a physics department. And so I think what this is doing right now, particularly in the United States, is there's really a camp of haves and have-nots. That is, there are the universities who can fund the resources for their political science departments to have big computational tools, and there's some, frankly, that cannot. So that's a sort of a Gini index comparison. So I think if I were a senior administrator at a university, and I never will be, thankfully, I would be very interested in how I could help and my social science departments leverage their research with more computational tools or more access to computational tools. So here at American University, we don't have a School of Engineering. So, I've been very proactive myself on procuring tools for the people I work with and so on and so forth. So the role of a data center like the one at UTD is going to be critical to the university, any university's success. I'm sorry about the reference to Renmin. I gave a similar talk a few months ago there virtually. They just founded a new data science center at Renmin University, so that's a nice notable achievement. So journal scholarship is going to change too, and I almost took this slide out, but I think many of us are sort of interested in this, and we might want to talk about this. So the model of journal publishing is almost becoming obsolete. So the idea that that we, and this is a few bullets down, that we academics, we give these commercial entities, right, including university presses are often required to be profitable. We give these commercial entities like Elsevier and Sage and so on and so forth, we give them free product that they sell back to our university libraries, right? And that's just a bizarre idea, right? And I think the thing that keeps that alive is that it's really important at tenure promotion time, and that's where academics get the most old-fashioned, right? We say we're modern in many, many ways, and we are, but when it comes down to that process, that's when we revert to mid-20th century thinking. But it's interesting because I got sort of curious about this, and it turns out that academic journals were created, as you see here, in the 17th century because at the time it took so long for books to be physically printed and then bound and then distributed, the knowledge got stale. At least people felt that way. So the idea behind original idea behind academic journals was to get knowledge out to people faster. Okay, so I think that's a great thing. By the way, the average time to first decision at political analysis is 37 days, and the average time to final decision is 60 days, and we've worked really hard on that. Another example of where that's important is that many medical journals, and I've had experience in this regard, you get 2 weeks for a revise and resubmit. And it's the idea, if this thing is going to be published, if this thing has value, we want it out there in the medical community as quickly as possible so we can promote better health and save lives. I think this idea that and this is so true in political science, and I'd love to hear Harold's thought on this as an editor at multiple journals, is the idea that the journal review process takes a year or two at many journals in political science. It belongs with the dinosaurs. And it's particularly, in my view, unfair to junior scholars who are either graduate students going on the job market at some point or assistant professors on the tenure clock. This is just, not a great model that we have in political science at the moment, and I'm hoping that changes soon. And, other fields more routinely do things like post-it archive and other similar similar places. And I have to say something rather cynically here, that we also live in a time in many of our social science fields where the achievement of a publication actually sometimes means more than the actual content. And what I mean by that is I know many, many people for whom they would rather have a very incremental piece in a top journal than a huge fundamental breakthrough in a medium term or medium rated journal. And that's just sad in my view. We can talk about that later, and I'm sure Harold has lots of good observations about that. The other thing is, here's another sentence I need to update, but the data century affects us on teaching, right? So the freshmen that you saw this semester, right? They were born after the internet was created. They were born after, sophisticated mobile technology was in all of our hands. They were born after 9/11. They were born at the end of after the end of the first Cold War. Well, that's okay. We have a new Cold War, right? They get a flavor of that now. And importantly, and this cannot be overstated in political terms, the 24-hour constant delivery of news cycle. So your students, your undergraduates, whether you're a teaching assistant, a professor, whatever, they have a completely different experience growing up than you did in terms of technology and in terms of politics and so on and so forth. They also sit in the classroom where they're wired into their social environment, their social network every second that you're lecturing. So, that means they can also fact check anything you say. And unfortunately, some of what they'll get are actually not facts, right? We know that is a problem. I've noticed over the years that they, or mostly their parents, want more value out of the college experience, meaning value in the vocational job sense. I like this point. I've seen several surveys that showed, there's another typo. The students really miss the on-campus experience. And I know here at AU, they were very anxious to be back, and they want their social environment. They want to be in an actual classroom. I'm sure we're all experiencing versions of that. There's another development here, at least in the US, and I haven't seen evidence of this internationally, but universities, particularly private universities, are increasingly tracking everything undergraduates do with their phones. So at many places, they register their phone as freshmen, and they're tracked by the university. They sign some legal document that they don't read, right, with lots of small fine print. And the university, and the universities, they claim that this is for the benefit of the students, but they know when they're in their dorms, they know when they go off campus, They know when they're in the classroom, when they eat, and so on and so forth. So my cynical comment here is George Orwell was unimaginative by comparison. So very few 18-year-olds know that they're being tracked at this level by their universities or colleges. Some ongoing big challenges. So I'm talking about for the world, not necessarily just for us. So most of the world doesn't understand the real challenges of living in the data century and how it affects their lives. Data quality is an ongoing issue and feature. Just because data are large doesn't mean it's good, right? You know, there's a confusing set of big data technology, and this goes back to my point about learning about something new almost every week. You can find misuse of readily available free software tools. You know, there are dangerous security holes and dangerous people out there that are expert in these technologies. And converting, you know, these sources into actual insights and results. Well, that's what most of us or people I know do for a living, but that's not what most people do when they get home from a different kind of a job. And of course, communicating to a general audience is always a challenge. I want to end up by talking about two sort of ongoing projects that I have that lead to big data computational challenges, and then I'll turn it over. I'll do this fairly quickly. I think I'm a little bit over my time. So I've been interested in spatial data for quite some time. It has a set of challenges that are slightly different. So the setup here is we'll just do a linear model where S is a set of physical locations, lats and longs or northernings and eastings, and Y S is a set of outcomes you care about. So ideology of a person at this location, disease status of a person at this location, and so on and so forth. So then you can stipulate a mean structure, so you can put covariates on that and estimate betas. And then it's typical to put a mean zero stationary process on there that captures spatial association. I'll be more detailed on that in the next slide. And then, of course, there's an error term. And these all have S's in them to remind us that these are spatially relevant versions of this linear structure. We can rewrite it with the normal assumption. And what you do in this setup is you decompose the variance covariance structure. And so this H of phi ij for the ith person of the jth location, say, is a correlation of H and its geographic distance in the following way. So buried in there is phi, which is a decay, which is the rate of spatial decrease with increasing distance. So the further person A gets from person B, right, we want to downweight their influence on each other. Sigma squared is called the partial sill. So that is literally the distance that affects the decay. So the decay is a function, and the sill feeds into that. The partial sill feeds into that. And then there's a thing called the nugget, which is the distance as the difference goes to zero. That's the variability that will always exist because people are different people. So this is a pretty classic setup. What we're generally interested in is a smooth density over space, over geography, and that typically means that we need to make predictions at unobserved sites so that we can have a smooth structure. And so in this notation, those are S sub 0 instead of just S's. And the way that I've done this in the past, and I'm continuing to do it, is a thing called Bayesian kriging. Basically, this is a smoothing operation. It's a Bayesian operation, obviously. It actually comes from mining, that is like digging up metals originally, but it's been applied in a lot of places. And so what we end up worrying about a lot of the time is the things down at the bottom, like the mean square error between the unobserved, right, and some predicted value f of y. And that's, of course, is a function of the smoothing process. I'm skipping over some details, obviously, based on time. So, typically what we want to understand is a posterior mean at these unobserved points from the smoothing function. But what this whole setup lets me do is get the expected value and the variance of those unobserved points given the observed points, right? So that it's an assumption that things transition smoothly over geographic space. But in one a data set that I've had to deal with recently, I had, as you see here, 25,000 training observations and then 250,000 forecast points. That's the S sub naughts, right? And the 25,000 is the S's. And in that process, what I needed to do, as you can see from the expected value and the variance up there, is I need to invert that variance covariance matrix. Well, to invert a 25 by 20,000 matrix, that's over 300 million calculations, single calculations. It turns out that's hard. And when you get to this point where the operation is that big, where the data are that big, surprising limitations come up. So surprising limitations are not just the time that it takes even a high-speed computer to do that, but how does the computer move things in and out of memory? How does the computer physically combine the operations and so on and so forth? And so you end up with some hardware challenges as well as software challenges, which is interesting. And then when I extrapolate to this omega y matrix, that's 25,000 by 250,000. And just to do a multiplication of that onto some conformable matrix is over 6 billion calculations. So I've learned loads and loads of matrix tricks over the last couple of years, matrix algebra tricks that I didn't know before. And it's interesting because I was an undergraduate math major. I took the classic matrix algebra course, and that was fine for me in terms of linear algebra knowledge all the way through a PhD in statistics. And so this is the first project where I really had to go back and dig up linear algebra, matrix algebra theory that I had not seen before. A good example of that was about 3 years ago, I want to say. There's a fantastic paper by Terence Tao, who's a very famous mathematician at UCLA.
Yeah.
What's that?
No, it's a youngest field medalist.
Yes, he's a field medal winner. He's one of the most famous living mathematicians. He and two physicists discovered a matrix relationship between eigenvalues and eigenvectors that nobody knew about. And it should have been in textbooks 20, 30 years ago. Well, it turned out that helped me a lot, that paper, because it has a fast way to go from eigenvalues to eigenvectors. And so I've been digging up matrix tricks to circumvent problems like this. I have a data set that I can't even come close to doing this model with because I would have to invert a 3 million by 3 million matrix 10,000 times in the Gibbs sampler. So I'm nowhere close to being able to use that data set, although I'd really like to. It's spatial. It's voters in California. No, that's not true. It's voters in the United States over time, and I've been working with the California data set most recently. Really quickly, the second one, I'm not going to belabor this one too much. I've been, for the last 10 years, I've been doing work in what's called Bayesian Nonparametrics, which is a weird phrase because it's kind of a parametric field. Basically, I'm not going to go through all the equations. I just want to sort of paraphrase this and get to one important point. What you do in this literature is you don't have they're Bayesian models. You don't have a single prior. You have a family, an infinite number of priors in a family, like all normals with mean 0. And in the original papers, which weren't very data-oriented, they were theory-oriented, people like Ferguson and Antoniak showed you could have all the priors, the infinite number of all priors as a prior, and you just average over them. So more recently, what I've been trying to do is integrate a clustering product partition model into this, where I can estimate clusters in this context, as well as the Dirichlet process. What that means is that in the sampler is going to walk through cluster space And each time it defines a cluster, the hybrid Metropolis-Gibbs algorithm will define a linear model in that cluster. So the Dirichlet process in my context serves as a random effect component. And so it's going through different cluster space. Well, that doesn't sound too hard until you start thinking more about clusters. And so so here is just an example. Suppose you have 4 subjects in your data set, okay? Well, it turns out if you have 4 subjects, there's 4 cluster classes and 5 configuration classes. So you can have everybody in one cluster, everybody in their own cluster. You can have a 1-3 split or a 2-2 split, or you can have a 1-1-2 split. So that's 5 configuration classes for 4 clusters. So in this notation, it's BNP. So B41 is 1, B42 is 2, B43 is 1, and B44 is 1. Okay, well that's pretty straightforward, but that's only 4 people in your survey or 4 countries in your study. So looking at this slightly more mathematically, so for n equals 4, we have these cluster classes. There are these configuration classes, and then there are 1, 7, 6, and 1 partition types. Okay, so the number of partition types is actually given by this equation here. So in the example, is just adding up these numbers here, 15 possible partitions, and that's given by the Bell number. Okay, so the Bell number for n equals 4 is 15. Now the problem with Bell numbers is they get really big really fast, more so than any other mathematical process that I know of. So if I had 30 people in my survey or 30 countries in my study, whatever I'm looking at, I would have 1 × 10 to the 24 different partition types. Okay, now 1 × 10 to the 24 sounds really big. It's bigger than you think. That's approximately the number of known stars in the entire universe. Okay, so that's the number of partition types to have the sampler go through, meaning it's basically impossible. So this is a I've been working on some computational tricks, some restrictive assumptions to get my sampler to go through a reasonable number of clusters. And another problem with this is visualizing cluster space for like here's cluster space for n equals 4, but visualizing cluster space for n equals 100, 500 is just our brains just aren't wired that way. So just to finish, life is complex, data-oriented, more technical than previous humans ever had to experience. Every field is a data science field, including political science. But even the humanities are becoming data science fields. So the digital humanities is a phrase that gets thrown around, is a really, really interesting area that is quantifying, various literary, historical, and whatnot data is a very active area of research, qualitatively and quantitatively. And I'll stop there and I'll go back to where I can see people.
Well, great. And looks like we need another 2 hours, Jeff. For each of that study needs another hour for each. Thank you for opening up really big challenges. Now, let me introduce the giant here to take up the challenges that you just presented. Allow me to introduce Professor Harold Clark and to discuss this topic. And Dr. Clark, and how much time do you need?
Oh, I don't know, probably several days, given all the interesting topics that Jeff raised in his very stimulating talk. I want to begin by thanking Jeff for the talk. It's really very, very interesting. And the comments that I have and the questions that I raised are really quite various, because the issues that the talk raises are various. And these are not in any particular order, but I'll start off with one that has to do with the dissemination of knowledge. that Jeff raised as a journal editor at Political Analysis, which of course is a political methodology journal, a premier political methodology journal, and one of the premier journals around, has been for some time. And he was talking about the time it takes, not just for political analysis, but for other high-quality refereed journals to actually, go through the process of reviewing a manuscript thoroughly, and then checking to make sure that the analyses that are presented are accurate, the data are real, and actually getting this information out to the scholarly community. And as he described it, it's horribly slow. It's really, really slow. And it has been, and in fact, I would argue as a person who's been a journal editor and began as a journal editor back in the 1990s, that in some ways, it's actually worse now than it used to be. And particularly not from the point of view of the scholars, but the point of view of companies. Like I work with Elsevier Publishing, don't mind mentioning that, and they just actually became worse and worse over time. And so this is a real problem. And for senior people like me, very senior people like me, I've turned increasingly, just for fun often, to publishing results as blogs. For example, work I've done over the last year on the COVID crisis in the United States at the state level. I didn't even bother trying to publish that in journals. I just put it out in blogs. And there are several, blogs that political scientists, which is my field, pay attention to. And I can do that in a week or two at most, and reach arguably a much bigger audience much faster than I could begin to do going through a 1 to 2 year process with a regular journal. And I'd be interested in what Jeff thinks about some of these blogs, like the Monkey Cage, for example, with the Washington Post, which we tried to set up a link with electoral studies many, many years ago. Wasn't successful. The LSE blog in England, more commercial quote unquote blogs like The Conversation, which is available not just in the United States, but Great Britain and even in smaller countries like Canada. And so I'd be interested in what Jeff thinks about the use of dissemination outlets such as blogs for getting the word out there quickly about your research. But just before I finish, I don't see this as you can still publish in journals if you want to, but if you want to reach people quickly and really have a conversation with a lot of people, for example, some of our blogs that we've done on elections, we have nearly 1 million clicks on these blogs that we've done, that Paul Whiteley and I have done over the last 4 or 5 years. And so what do you think of that, of those outlets, Jeff?
I think it's wonderful. I mean, I think it's great that we can communicate on that level now, both to other political scientists and to policymakers and opinion leaders and so on and so forth. But that is not a venue for a junior professor trying to make promotion and tenure. Or other people, like we have term professors here, and they're on multi-year contracts, right? So they're always under the gun. And until we figure out how to reward people at that stage of their career, it's always going to be confined to people like you and me, Harold, who will never be promoted ever again.
Right? Might be demoted, but in my case, I will.
Yeah, I mean,
demoted.
So I love the idea that political scientists have people listening to them, and that's always been one of our problems. And frankly, that's always been an area where the economists did better than us, right? And now I would not say that that's necessarily true. But like I mentioned in the talk, universities, faculty, we get super traditional around promotion. issues.
Yeah, I think that's absolutely right, and that the criteria that we use for promotion and tenure, which of course is one of the key things that we do, is remarkably unchanged since long before I became a professor even. And of course, I think you're absolutely right about that. And we really don't know how to grade or to use information about a faculty publication, quote unquote, in these new venues.
No, we do not. You know, I recently wrote a tenure letter, and the department chair offered to send me the person's book. And I said, no, I don't want the person's book. Send me a PDF, right? My office is packed. You know, so like that's another traditional thing, that you have to have something in, you know, in your hands like that.
That's right. And another thing closely related to this, and you mentioned economists, and I served for a while as director of social sciences, social and economic sciences at the National Science Foundation. And one of the things I found very quickly confirmed my prior, that economists were just so much better at publicizing their work around academia and publicly than were other social scientists.
Yes.
And one of the things I tried to get people to do, people like Henry Brady, for example, and Skip Lupia, who's now at the NSF, was to try to do things within professional associations of political scientists, in this case, to actually get out into the public arena more. And I knew that Henry was interested in this, but we largely failed. We really still have not, you don't see us on the nightly news nearly as much. You'll still see economists. And so that's one of the things, too, in terms of communicating knowledge, whether it be about big data projects or regular, sort of what I call regular data projects in political science. When you get beyond economics, social scientists, I think, still do a pretty bad job.
Yeah. Another thing economists do is they give each other more prizes.
Oh, yeah. Prizes for all.
Yeah.
I can remember Nancy Lutz, who was the program director for economics, came in to me and proudly said that Professor X had just won the Nobel Prize in economics. And I said, Nancy, with all due respect, he did not win a Nobel Prize in economics. There is no Nobel Prize in economics. There is a prize which is an honor of Nobel. It's not the same thing. But no, they're just super good at that, and we're quite bad.
When I was president of the Society of Political Methodology, I realized that we were award challenged. So I went to some economics sites, you know, associations, whatever, and I poached some of their titles. So I created the Emerging Scholar Award, and I realized it cost us $50 for a plaque every year, and that, you know, so we could definitely afford that. And then I ran out of ideas, but we should give each other more awards. Sorry.
Yeah, well, I think that's exactly right. So that was, you know, sort of one line of questioning that I had. Another one has to do. This is really a comment. As you were talking about this emerging field, which has become known sort of generically as big data, and at our school, everybody's got a big data program, and Carl is teaching big data courses and so forth. But I want to talk just for a moment for our audience, especially for the students, tell them a little bit about what big data looked like when the Beatles were playing in Shea Stadium half a century ago. And at that time, I just started university and was doing an honors degree. I was doing mathematics and political science. That was sort of an odd combination at the time. But one of the things that my school did, which was the University of Western Ontario up in Canada, I foolishly turned down an offer from my parents to try to get me into Harvard, which they had some insights to. But being a stupid little Canadian, I decided to stay close to home. But anyway, all that aside, one of the things my university did was to go to Yale University and hire one of their recently minted PhDs to come and teach us knuckle-dragging Canadians about American political science, which was really quantitative analysis. And so indeed, I signed up for this seminar. And in Canada, seminars like that went all year long. I mean, you'd start in September and you'd end in late April. And so this guy, his name was John Shingler, who went on to McGill University later, had us use ANES data from the ICPSR archive to to analyze election, the quintessential, the canonical data set in political science at the time, and in some ways still is, at least for electoral behavior scholars. And so at that time, that was big data in those days. But how, there are all sorts of questions which are similar to the questions that are raised now about, how do you access those data? How do you actually get them? Well, of course, they've been gathered in the first instance through a sampling procedure, which is well known at the ICPSR. But we didn't, especially as students, we didn't have those data. So what we did was to communicate with the ICPSR, and they sent us a code book. That physically sent us through the mail. In those days, there's no internet. That was decades later. No PDF, but just sent us a bound code book, and each student decided on a topic and then decided on which variables would be relevant for studying that topic. And I decided for some reason that I would study the 1960 election of John Kennedy and Richard Nixon. I wanted to study voting behavior in that election, but for some reason I wanted to study the voting behavior of farmers. I have no idea why. But so what I did, this was big data in those days, was to identify my variables, and you had to limit yourself to make it really sort of easy, for us to analyze. The number of variables that you could get within 80 columns, like what was one computer card in those days. And so all the students, there were about 8 to 10 students in the class, we all did this, and our professor sent our request back to the ICPSR, and then a couple months later, we all got our data. Now, our data did not come to us, we did not download it. It wasn't on a flash drive, it wasn't on a floppy drive, it wasn't on a 9-track tape. It was in a shoebox of so-called computer cards. Most people, I think, at this talk this evening, and certainly in the classes I teach, have never seen a computer card. They have no idea what that is. And so whenever I teach a class on campus, I will always, at the beginning of the class, one of the first things I do, if I'm doing a little historical thing like tonight, I will bring along a computer card and wave it in front of the students. So, okay, I've got my data. How do I analyze them? And again, this is a big deal that you were talking about. In those days, those big data, how did I analyze them? Well, I had to use, there were really sort of 2 tools. One of them was to use a computer, but we had no software that was dedicated for this kind of analysis at all, let alone doing like regression. We never heard of regression. We just wanted to do crosstabs and compute chi-squares and so forth. So what we had to do on Saturday morning was to go and take classes in Fortran in order to learn how to actually analyze these data and to do manipulations, which I'll come back to in just a moment. But a lot of my colleagues in this class, Fortran was flying over them pretty fast, and so we asked, is there an alternative? Is there some other way we could analyze the data? And our professor said, oh yeah, go over to the computer center, and we had like one computer on campus, and some associated machines, one of which was something called a counter sorter. And what this thing did was you simply, if you wanted to do, say, a 2x2 crosstab of gender against voting Republican versus Democrat, you would just sort on the gender variable, and the cards would, you would set that up. The cards would go into the different bins, the two bins for men and women. Might have been columns, column 40 or whatever it was on the computer card, and then that would be the sorter, and the counter would just say how many men you had and how many women. You'd write this down on a piece of paper, and then you would take those two groups and sort them again, but say on column 10, which is how they voted in the 1960 election. That then would give you the numbers you needed to compute a Pearson chi-square, and you would compute that Pearson chi-square. How? Well, we had, and I was quite proud of this, we had to do this, you know, we had to have a slide rule. And so I had a slide rule, but not just any slide rule. I had several friends who were taking engineering degrees, so I had one of these fancy engineering slide rules. So this was big data. This was big data back in the mid-1960s when I was, you know, starting my so what would become a social science career at University of Western Ontario. But what makes this real, and we've made, of course, incredible progress since then, and Jeff, of course, is telling us of all the progress we now need to make again. But there's one area coming out of this I want to, again, this is just a little bit of a rant, where we haven't made progress. That 1960 A&ES election study was arguably better of its type than what is being done in 2020. And one big difference is we're paying orders of magnitude more to do the same research. That 1952 Buick that your grandfather bought is still the prototype for what we're spending a lot of money on in survey research in social science. And we tried to break loose from this when we were doing the British election study by doing internet surveys every month throughout the electoral cycle and communicating the data to people on our website within days literally within days of receiving those data. Recently, I talked to people who are doing the 2021 Canadian election study and said, hey, I know you're doing this, and the election was September the 21st. Can I get those data? And they said they won't be available for a year. That is unconscionable. And this, of course, is not a really big data set, but it's much bigger than the ones that we used to have. They'll have a sample size of about 30,000 Canadian voters scattered across the 338 constituencies. Still a discernible improvement. And speaking of that, one of the projects that is not a big data project, it's a little data project, but it's a much bigger data project than these traditional election studies, is something that called the Cooperative Congressional Election Study that Brian Schaffner, another one of my colleagues, formerly at the NSF and now at Tufts University as a chair at Tufts, he is doing the CCES with a colleague at Harvard, and they gather 60,000 stratified samples of 60,000 voters or eligible voters, and that allows you to do multi-level modeling in a way that would be undreamt of with the traditional A&ES type surveys. For example, the power of that kind of design, and it's a little design, but still an innovative one by political science standards, is that you can study the attributes not just of choices or of choosers, but of choices. And one of the things we've been doing recently has to do with gender. Does the gender of a candidate matter? This is a multi-level modeling problem, a hierarchical linear modeling problem, if you will. And we have been doing that, but we couldn't do it with traditional data sources. So my point, my general point is there's an awful lot of work to be done in terms of improving social science data, even within the traditional ambit. Now, the traditional ambit, though, isn't all bad compared to the kinds of data that people are gathering as big data scientists in political science, at least, because those traditional projects tend to be much more theory-driven. And rather than just saying, oh, well, I can get data on tweets or whatever, they say, well, no, I want data on particular theoretical perspectives, whether it be spatial models in the theoretical sense, not in the sense of geography that Jeff is talking about earlier, or whether they be valence politics models or whatever. And so I think one of the challenges, and I'd be interested in hearing what Jeff has to say about this, is how can we inject more theory, if you will, into our big data gathering projects, where it seems to me, I may be wrong on this, but we're relying very much on what other entities, whether it be Google or a bank or whatever it might be, some Wall Street firm or a university or whatever, are gathering for us. Jeff, I've talked quite a bit here. I'd like to hear your comments on that.
Well, there's a lot to comment on there.
Yeah, there is. And I apologize for going on.
Yeah, I think the role of theory should not be diminished by the size of the data. Just because you have a lot of data doesn't mean you have a lot to say, right? Certainly in the context of a social scientist or a political scientist doing their regular work. Where theory really comes down to it for most of us is what to put on the right-hand side of some linear or nonlinear regression specification, right? So the thing on the left-hand side is the thing we're interested in, right? And we want to explain. And the things that go on the right-hand side should come from theory, right? So in your world, Harold, right, there's about 10 variables in a voting model you have to have. And if you don't have them in the model, the reviewers will drive over to your house and beat you up, right? Almost all literatures have some version of that, right?
Yeah.
The take that I really like on it is something that Ed Leamer wrote about in the 80s. Specification Searches is the name of his book, and he's got a great article called "Let's Take the Con Out of Econometrics," which unfortunately never happened. For sure. And by the way, nobody really listened, and now he studies real estate. But so Leamer's way of talking about this really resonates with me. Is you have in front of you a set of variables, and you have the under the horizon variables. And those are the variables that your literature says you have to have when you're studying Y on the left-hand side, right? And if you don't have those, you better have a really good explanation for why you're leaving some or one out to your readers or reviewers, right? And maybe you do, right? Maybe you think it's no longer germane or it isn't germane to your, but in general, you either have to have those inside the horizon variables or explain why you don't. But if you only did models with those variables, you're not contributing to science in any way. You're just telling us stuff we already know. So you won't get published for that reason. So you have to have some over the horizon variables, right? To contribute to knowledge, to get published and fame, fortune, tenure, promotion, whatever. And so the game is really about not just which variables you have in that over the horizon set, but how they're measured. Right. So the ANES has what, Harold, like 6 or 7 versions of ideology now, 5 point, 3 point, 7 point, whatever. Right. Which one do I want? Well, I want the one that fits best, probably. Right. I know I need ideology, but so how does big data change the game for over the horizon variables? And I think it has the potential to change the game where you can specify an over the horizon variable that wouldn't have worked out in other contexts, right? Maybe the measurement wasn't granular enough that when you had a 500 subjects, you weren't detecting an effect. But maybe if you have 100,000 subjects, you have the power to detect and hopefully defend an effect. So I think that's sort of at the intersection of what you're talking about and where big data helps us out a lot. Now, one of the reasons I'm philosophically Bayesian is in all Bayesian models, asymptotically, the data always beats the prior, right? And sometimes, however, looking at going the other direction, sometimes we put data on a pedestal relative to prior. And certainly a lot of people would say that the data are more important. But that's not necessarily true. Suppose I have a small data set, or I have a data set of modest quality. Well, then the priors are going to be really important, and I can still model. And that, so like, if I take my literature and I build a prior on known things in my literature that are accepted, I can use a weaker data set and still have possibly an efficacious posterior model result, right? So, you know, so built into Bayesianism is this data size mechanism automatically that's there. So I think, you know, looking at it in the other direction, I think it's an underappreciated thing that being a Bayesian means that you can have the literature outweigh a modest data set in some regard.
Can I ask some questions?
Carl, do you have a question?
Yes, I have a hand up. I want to line up to ask questions to both of us, both of you. And this is really interesting. I think this is the best talk so far for the colloquium. Now, I want to cite your earlier slides, Jeff, the ability and amount of or the ability of scientists or whatever, whoever scientist, political scientists, to answer the question is getting lower every year because the data is getting much bigger every year, and so are the questions raised or begged by this increasing volume of data. That proportionally, our ability to answer these questions is lower every year. And now I want to also cite Dr. Clark's question, also remarked about how much we can actually improve in our efficacy, citing new efficacy to answer questions better than 20 years while we're getting better computing power, getting access to data much faster and bigger data much faster, much more efficient, much more efficiently. So this if I look from the data science educator's point of view, and first of all, I will take another perspective. Now we traditionally try to answer the questions of why and how, and which is like inference. We want to draw inference, trying to explain the phenomena, and we're trying to answer the question why voters would select this candidate, etc. But now with data science coming aboard, we try to predict. We citing Leo Brayman, and we come to the result predicted first, then to go back maybe later to talk about the black box that can help you the selection of the best algorithm to come to the prediction. What I care about is how accurate I can predict the result. Then there could be inference lack, or it could be short of inference, short of explanation of this black box. What I care about is I want to predict, and particularly in applications, particularly in problem solving, for example, and how much I can predict this vaccine can reduce the death rate and reduce the symptoms, versus why, and this combination or this model with the range and variables could get the best result. So that will be something still seeing a wider gap between the two explanation versus the other side is a prediction. There is a development in data science about bridging this gap, basically this is what Leo Braidman started in 2001, and how do we narrow this bridge to get predicted results well explained with the best model. So this I think this best answers for from both Jeff and Harold, and from your perspective, and particularly you spent you published a lot in terms of parameterization and building best models to explain the theory, and so this will be something I think I really like you to chime in, to weigh in, and from your perspective.
Yeah.
Yeah, there's a lot to think about in that. I think part of what you're referring to comes down to deductive versus inductive inference.
Mm-hmm.
And you know, the sort of, I like the classic way of thinking about it, that science is both inductive and deductive. Right?
Yeah.
So as an example, no astronomer developed a theory saying binary stars could exist, binary star systems could exist. But someone observed a binary star system, and then they had to go figure out how that came to be and why it works, right?
Mm-hmm.
So, you know, they started with an inductive observation, and then they had to do deductive work. And, you know, I think there's a sort of a deductive mafia in political science that says, don't start with a formalized theory that, you know, your work is not any good. You know, I'm a big believer in, you know, you get a data set you're interested in, you know the literature, you explore the data set for a while, right? You look for features that you think might exist that haven't been in the literature. And that's kind of an inductive exercise, but we're not allowed to say that in our article, right? You know, a empirical political science article says, here's an important problem. Here's a new theory I developed. Here's the data set I got. Here's the model I ran. Here are the results, right? By the way, here's the model I ran, right? The single model I ran, right? We're not allowed to say we do specification searches. And so there's a bit of that. But contrast that with the kind of work, the big data work that your credit card company does.
Mm-hmm.
So the companies like that do classic data mining through gigantic data sets, right? With automated machine learning processes, right? Unsupervised.
Mm-hmm.
And they don't care about the theory. If they find that people who go to Whole Foods tend to spend more money on groceries than people go to Safeway, that's all they need to know, right? To make decisions they might make. And they don't need a grand theory to publish off of. And by the way, your credit card company knows so much about you, it's ridiculous. You know, so if you pick up a prescription once a month, they know you have a chronic condition, right?
Yeah.
Mm-hmm. If you go to the liquor store twice a week, they know something about you, right? You know, if you're Harold and you spend a ton of money on gasoline for your car collection, they know something about you. Right? So you know, but the way they approach that knowledge is reasonably atheoretical, and it doesn't need to be theoretical, right? But we have a culture, of course, and this is I think some to your points we're referring to. We have a culture that dictates, at least in how we write, that we started with this grand theory that we're trying to publish or support.
Mm-hmm.
Harold, did you have any?
Well, I just sort of a couple. You mentioned earlier Ed Leamer, a graduate of the University of North Carolina at Chapel Hill, by the way. About the same time I was living there. There's a footnote on a footnote. But another name with a who's very, very important in this field of really robust statistics is really what we're talking about. Of course, is David Hendry and his great 1980 article, Econometrics, Alchemy or Science. That's another title that I love. one of the things that you mentioned, of course, was this idea of you have to have all the usual suspects on the right-hand side. And sometimes, with a fair degree of frequency, one of your reviewers at least will say, oh, you forgot Jeff Gill's variable, or you forgot Carl Ho's variable, or what have you. But a lot of the work that people like Leamer and Hendry, and then more recently, the economic sociologist who used to be at Stanford and is now has moved on there to Cornell. I don't know if he didn't get tenure or what at Stanford, but anyway, a guy by the name of Christopher Young is doing robust analyses very, very simply of just looking at all possible combinations of predictors and looking to see whether or not he gets a stylized fact or not that his, that variable X affects variable Y in all possible models with that set of right-hand side variables. I'm surprised that that is not used much more often than it is, because there's really, as you know, sort of two approaches to this. One is exactly that. Do I get stylized facts, as the economists say, no matter how I do this, variable X matters, and it matters a lot. Or the other side is what I call the perfect model approach. The only thing you can talk about is the perfect model and the effect of X in that model. And these are two competing, you can see them sometimes even in the same article. But nevertheless, I just wanted to put that in there as a footnote on how sort of what's usual practice. But I did have one question for Jeff, and that has to do with sampling. Mm-hmm. And he showed me and showed us, all of us, one of the slides. It's got, I don't know how many zeros for different kinds of levels of data that we're gathering. And those things are scary big. They're really scary big. And I'm wondering, in the big data field, my approach to that typically would be just like I said, oh yeah, there are 180 million voters or whatever. I'm just going to sample. I can talk Skip Lupia into giving me enough now from the NSF, enough money to sample 5,000 of them, whatever. And I know about 1 over root n, and I know these kinds of ideas. So to what extent are people sampling out of these huge data sets, Jeff, in order to try to make this a tractable problem for most people, the kinds of computing resources they might have?
Oh, yeah. I mean, it's clear that people are doing that, Harold. I've got students that do that out of necessity, and that is the resources that they can physically have at that stage of their career. Mm-hmm. One of the things that that I came up with in that spatial project, or the ongoing spatial project, is spatial bootstrapping, where but what I'm doing is I'm bootstrapping out of the full sample, repeatedly, and then combining the bootstrap estimates. So what it does is it breaks the problem. I'm overgeneralizing, but it breaks the problem down into manageable analytical units, and then recombines at the end. There's a technology also called data cubes that does something similar. Mm-hmm. And so a classic big data strategy is to break it down and build it back up, if you can do that in a principled way.
Yeah, bootstrapping. Yeah. Maybe I can invite any questions from the Taiwan side. I don't want to monopolize the time here. And Peter.
All right. I'm here, but first of all, I'm honored to be in the midst of this great intellectual exchange and conversation. And of course, some of them might be over my head, but if I may, I can switch the channel to another question. I have a question for Jeff, because you mentioned about the haves and have-nots, right? Or the Gini index, that the metaphor that you mentioned. of the infrastructure, if I was right, required to deal with the big data in a university environment. And so I understand that there are many political methodologists out there, but in terms of teaching and research in a more general sense, besides the infrastructure issue, I think there's a psychological barrier or a gap or threshold or whatever you may call it for some traditional social science students to cross over. So many of them select social science as their field of study, not only because they're more interested in studying people, but also the methods or research method that they feel less uncomfortable with, like math, stats, or even advanced math, advanced stats. So why we have this data, this colloquium, one of the purposes that we try to introduce this methodology to encourage the students from that, what I call more traditional political science side or training, and then to make them open their eyes and their minds, and then to accept the more, we are living the digital era and the big data era, and we have to know all about this. So, and then we have to keep the pace, not just students, even our with faculty members. We have to keep the pace so we can deal with that. Otherwise, all the things that you just mentioned would keep happening. Keep lagging, lag behind and left behind, all those things. So anyway, so what I'm going to ask is, do you think this disparity problem, be it physically or psychologically, will it eventually get better as it evolves, or how do we alleviate this? Yeah, from your perspective. Yeah, thank you.
That's a really important and good question. If I go, you don't mind if I go first, Harold?
No, yeah.
So okay, so in terms of like how PhD students, how graduate students enter this equation. So if you go to graduate school, a PhD program in statistics, they throw you into a mass stat sequence, usually out of Casella and Berger, where you need to be fluent in 2 years of calculus and a year of matrix algebra day one, and they're not going to teach that to you. If you go into an econ PhD program, you go through the micro series, right, first year, and in both stats and econ, you get a big scary weed out exam at the end of the first year, right? And do that because unlike the natural sciences, those students don't need bench space, right? So you can overpopulate your PhD program and then weed them out. And that's sort of the philosophy in stats and econ. In fact, when I was at WashU, the first year econ students were in the power plant building with the smokestack. Like they weren't quite human yet. So, but unlike that philosophy, political science, political methodology operates differently. Most political methodology students, that is a student that eventually takes a third year or whatever year exam in political methodology, 90% of them come into the PhD program not knowing what methodology is, right? And the social sciences do a really bad job of moving college seniors to first year PhD students, right? There's a big gap there, which is why we have boot camps and things of that nature. So a student can come into a political science PhD program and they don't have that big scary end of first year exam on technical material. They can ease into methodology, right? And if they find that in that process they really don't like it, they can ease out of methodology. And so it's a much less threatening path, in my view, than what stats and econ do. And so I really enjoy it when a student is in my office saying, I never knew I could do this stuff, right? And now I'm thinking about taking the methods exam, and I find that incredibly rewarding. Just that you've turned someone around on an ability they didn't know they have because it wasn't imposed upon them in a sort of militaristic way. And most first year method sequences in political science are pretty gentle. I think we'd all agree, right? You rarely get past the linear model by May of your first year. So you get inference, cross-tabbing, you know, a little bit of probability theory, so on and so forth. So I think we do a better job at turning people around than those other two. Well, you know, they don't have to. This is actually the answer. And I think that I forget what else I was going to say, so I'll turn it over to Harold.
Yeah, I think you're absolutely right on that, Jeff. One of the things that I found teaching at UTD in the School of what they call now Economic, Political and Policy Sciences is that when I teach a methods class, whether it be an introductory one or one that's more advanced, quote unquote, is that I get students from several different fields. But typically I don't get many economists. They tend to keep their students to themselves. But other programs, whether it be criminology, public policy, sociology, and even people coming over from the business school, from the Gill Management School, I get them, and I really find that's fun, having people doing papers coming out of different backgrounds. And I find there's a lot of commonality exactly along the lines that you've described. It's the economists that are very much the outliers again with regard to this. And if we were to look at that more closely, I think there, as you say, there are pros and cons to this. There are pros and cons to this, the economists being rather brutal. But what that means is that the students they get really are probably pretty good at using these techniques, and they'll be able to do so effectively, where we still get a lot more variance in terms of what our product's going to be, despite our best efforts.
Mm-hmm.
What I was asking that, do you think either Harold or Jeff, that this disparity problem, what I'm observing, so because you think that the younger generation, yeah, they were born with those new stuff and the data generating stuff, the digital era. So you think this disparity problem will be, just eventually get better or not, or it's getting worse in the future if I'm not doing anything or we're not doing anything about it? Is it going to get worse?
I think the resource disparity is going to get worse in terms of between departments. Wealthy, mostly private universities have immense resources that they can spend on social scientists if they choose to. Then you go down the next tier, and it's not a gradual drop down in resource, particularly computational resources, right? That can be provided. It's a big drop, going from, say, at least in political science, say the top 20, 25 departments to the rest of the departments. And as the requirements for doing work get higher, I think that Gini index is going to get worse. And I don't see how that's going to change. If people can be creative, right, about how they train their students. So here's a good example. Anyone in the world can take Gary King's PhD methods course. Anybody.
Yeah, it's open.
Yeah, so why wouldn't you? Right? Is there a better one? I doubt it. I guess, a methodology program at a less resourced university has to work harder and be more creative is probably the answer there. And then the other piece that comes into it is grantsmanship, right? And supporting, and the structure of getting grants and whatnot. And, and the Gini index there is big too. I mean, when I was in a medical school for the better part of a decade, if you whispered in the hallway that you were thinking about applying or sending in a proposal, staff people would just descend on your office, and that's just the culture because it's soft money and everything like that. political science departments have a very mixed, heterogeneous record and ability to do that, to pursue NSF and other grants. It varies a lot, right, Harold?
It does. It does indeed. And again, as a sort of personal reminiscence, I remember when I was at the NSF, was in the era of the Obama stimulus. You remember that, about a decade ago, and money actually came down to my level at SES, and I think we had not a lot. We had about $40 million to distribute across 8 programs. The economists who were getting the lion's share already of the regular money insisted that I use the same proportional distribution for the 40 million. And I said, not on your life. What I'm going to do is to start off with an allotment which is equal for all of the programs, and then I'm going to keep some money back in my office for people to compete for across the programs. And the economists had just had a stroke about this. And I said, no, it's time that to use a phrase of a British Prime Minister, current Prime Minister Boris Johnson, it's time for us to level up. And so, I was trying to do that kind of thing on a small scale to try to energize and invigorate the ability of these other programs to have funding for good, for good proposals, which had reviewed very well, but there just wasn't enough money for them. And there really wasn't enough money in political science, for example. There was $8 million, and the ANES took half of that. So, I wanted to mention that as an example of what we're talking about. Now, if you're a political scientist and you are trying to get money, traditionally the outlets that have been available to you, they'll have been quite limited compared to what you might be able to, where you might be able to go, say, in the private sector, if you're a computer scientist, for example, let alone being someone who could tap into the vast resources of the NIH or something like that. So, and in recent years, of course, it's become even more difficult as politicians in Congress on the extreme right and extreme left both have combined to attack the social sciences in general and political science in particular as not being worthy of any government money. And so that's yet another hurdle that we have had.
It's funny, Harold, that you mentioned NIH, because the grants are so much bigger in that world than the NSF.
They are.
Yeah, I was once talking to an MD colleague in the hallway, and I mentioned that political science was 8 million, and she misheard me, and she said, 8 million, that's a pretty good grant. And I said, no, that's all of the grants.
That's it. That's all. It's actually half that for all the grants, because one is already earmarked.
But in her world, 8 million was a pretty good grant. Yeah.
Yeah. I've had exactly the same experience talking to people at the NIH, so yeah, it's a real problem. One of the things that we were successful in doing over the past several years was to go to the Gates Foundation, for example, private foundations, to do surveys. We ended up doing 40 panel surveys for the Gates Foundation, and they had their own particular interests in terms of modeling overseas aid, and I developed some models for them for that, and tried to test them with these surveys done in Britain, the United States, France, and Germany. But beyond that, I had my own interest as a political scientist, and so I would sneak, quote unquote, some questions in there that I knew could be used for other purposes. But even that can be difficult. And a good example, again, from this with the Gates Foundation was that one of the things, of course, one of their principal interests is generating, measuring, but also generating public support for overseas aid programs. government overseas aid programs. And it occurred to me that a lot of the aid that we donate, of course, goes to African countries, third world countries in Africa, and of course, a great many of those countries, sub-Saharan Africa countries, those people are, they have particular racial characteristics. They're black people, and we know from our research in political science that racial attitudes are really important for a lot of political attitudes and behavior. So I suggested that we take David Sears's racial resentment scale and adapt that for use in our gate surveys. So this has proved to be very powerful in the American context in work done with the ADS and the GSS and so on. I had a heck of a time getting them to do that, and the Gates people to agree to that. And the reason was they said, oh, but we would be looking to, we might get to see that people are biased. And they were wringing their hands. And I said, exactly. That's what we need to know. If we're going to understand resistance to overseas aid, this is potentially a really important concept, an important variable to bring into the ambit of our inquiry. And we finally succeeded. Joe Twyman, who was at UGov at the time, doing the survey, actually doing the field work for the surveys and so forth. Now with his own company, helped me out, but we were able to do it. But it was hard. And again, it's an example of a barrier to inquiry, which is quite significant when you try to generate money from private foundations or private entities that have very particular sort of worldviews.
All right, I think it's great dialogue. I wish I had more time. And Peter, do you have more questions from your side?
Yeah, I wish we have more time, but actually we have to let them go and let you go. It's almost 12 o'clock here in Taiwan, and so yeah, the time is up. So Carl, do you want to wrap up, and then maybe let's expect for the next opportunity so we can invite both of them to come aboard and to share with us more of their intellectuals. Thank you.
Yeah, thank you, Peter. I think I wish I have more. I have actually more questions too. I think it's particularly on Jeff's recent research and recent studies, and there's some suggestions and some questions. Yeah, but we have to wrap up. But before I conclude, I want to introduce to you. We have this is a series, and we'll have another upcoming webinar, which is only 2 days and away, and we will have Dr. Harold Clark back, and also he will join Dr. Chris Aiken from Princeton University. Last time he, for technical reasons, we cannot have him, and now we can have him back on December 9th, and US time, December 10th, Taiwan time. Allow me to share the screen and then introduce our speaker, which is on December 9th, and Dr. Clark will be here also, and excuse me, and that will be this one. Can you all see my screen? Okay, so
Carl, I think we're going to talk about discrete choice models, aren't we?
Yes. Chris is going to give a speech on titled "Getting the Politics Right in Election Research," and this is basically revisiting a method called multinomial probit, and I invited Dr. Clark back because he's also an expert in this, and he has been using this method actually back in those days when I wrote my dissertation, and back in those days, and that is one of the most computationally expensive or intensive methods. Then he introduced me to studying British elections. Now, Dr. Aiken is going to give another lecture on this and introduce a method to implement this model much more efficiently. And now this will be December 9th, and in US time, December 10th, Taiwan time. And please visit our website and to register and get the link to the webinar on Thursday and Friday in Taiwan time. And okay, I think I can stop here, and then this will be the announcement for the colloquium. And I want to thank Professor Jeff Gill and Professor Harold D. Clark again. This is a really wonderful opportunity. We can sit and bring these two methodologists and scholars in the same event. Then a great dialogue and a very insightful dialogue. Actually, this could be just the beginner of a series of talks, and they raise many notable topics that we want to pursue further, and maybe we'll bring them back and to inspire us more, to update us more with the latest advancements and developments, and so bring questions, but more importantly, bring answers to. All right, thank you. Peter, do you have any announcement to make before we conclude?
Yeah, that would be all. It's just a reminder, 2 days from now. Yeah, because this week we have two speeches, and we have a great guest today. I understand that this might be, you're already in your winter break, right? In the United States?
Almost.
Yes,
Yeah, right.
thank you, Jeff, and thank you, Carl, and thank you, Peter. It's been a real pleasure to have the opportunity to participate in this.
Yeah, thank you. It was an honor and a pleasure, and best of luck with the rest of the series. Chris will be a lot of fun, and he has very strange hours. He stays up really late at night.
Oh my goodness.
This is a perfect forum for him.
Yeah, same time zone as yours. Yeah.
When he was at Michigan and I would teach there in the summer, I would meet him. It was lunch for me, but breakfast for him.
All right. Yeah. All right.
So,
thanks.
It should be a very interesting talk. I know Chris as well, and he always does really good presentations. Very, very interesting. So be sure to attend if you get a chance.
Yes. Thank you. Yeah.
Yes. Thank you, everyone. All right. So that would be it for today for this talk, and hope to see you guys all again very, very soon. Thank you. Goodbye.
Thank you.
Thank you. Bye-bye. Bye-bye, everyone.
Bye.